Hi, could you tell us your name and tell us about your project? My name is Arthur Holly Compton. My project studies what happened when X-rays strike materials such as graphite. I directed a narrow beam of X-rays at a graphite block and measured the X-rays that scattered away from it. I discovered that some of the scattered X-rays had a longer wavelength and less energy than the original beam. I explained this by treating each X-ray as a particle called a photon. The photon collided with an electron and transferred some of its energy to it. This discovery became known as the Compton effect. What were you trying to do or find? I was actually trying to explain something that classically physics could not. Classical theory predicted that scattered X-rays should keep their original wavelength. However, my experiments showed that some of the scattered X-rays actually lost energy and provided a longer wavelength. I wanted to determine why that happened. I treated the interaction like a collision between two objects. The photon transferred energy and momentum to an electron, causing the electron to recoil. I developed an equation showing that the change in wavelength depending on the angle at which the X-ray scattered. My experimental results closely matched that prediction. Where did the project or experiment occur? The main experiment actually took place in Eads Hall at Washington University. I became the head of the university's physics department in 1920 and began the important measurements shortly afterwards. My equipment included an X-ray source, a graphite target, a crystalline spectrometer, an ionization chamber, and a sensitive electrometer. The source and target were kept inside a shielded lead box. I presented my explanation to students in November 1922 and to the American Physics Society that December. I published the complete results in 1923. What other significant events were happening around the world at this time? This experiment occurred shortly after World War I, when countries were recovering from the war and attempting to cooperate through the new League of Nations. The United States was also experiencing major social changes. For example, the 19th Amendment had recently given women the constitutional right to vote. Physics was changing too. Einstein had proposed the idea of light particles, while other experiments clearly demonstrated that light behaved like a wave. Many physicists did not believe radiation could act like both a wave and particle. My experiment provided important evidence that it could, however. Who else was involved in the project? Although I directed the main research, several other scientists contributed to the discovery and its confirmation. Charles Hagenau worked with me on studies of X-ray polarization. Peter Debye independently developed a similar mathematical equation too. Charles Wilson later photographed the tracks of the electrons that recoiled during the collisions. Alfred Simon worked with me in another experiment that examined the directions of the scattered radiants and electrons. Walter Broth and Hans Gregor performed an independent experiment in Germany that also supported the photon explanation. Earlier researches by Charles Barkla helped establish the X-ray problem that I was also trying to solve. What was your role in the project? I was the project's lead experimentalist and theorist. I selected the problem, designed and improved the equipment, performed the measurements, and interpreted the results. My most important contribution was connecting the wavelength chance to a collision between a photon and an electron. I used the conservation of energy and momentum to create an equation that predicted the wavelength change at different individual scattering angles. I then compared that equation with the measurements. This turned the photon idea into a scientific explanation that could be directly tested and proven. What impact did your project have on the physics community as a whole? My experiment gave physics convincing evidence that electromagnetic radiation could carry energy and momentum like a particle. At the same time, diffraction and polarization still showed that radiation behaved like a wave. Therefore, the discovery became important evidence for wave-particle duality. The Compton effect helped support the development of quantum mechanics during the 1920s too. I received half of the 1927 Nobel Prize in Physics for the discovery. Compton scattering is still important today. It is used when designing radiation detectors, studying medical X-ray images, calculating the momentum of radiation through materials, and building telescopes that detect gamma rays from space. What criticism did your explanation face, and how was it tested? Some physicists resisted my explanation because they wanted to describe the radiation only as a wave. Niels Bohr, Hendrik Kramers, and John Slater proposed that energy and momentum might only be conserved statistically across many events instead of during every individual collision. Alfred Simon and I tested this using a cloud chamber. We examined the directions of recoil electrons, and electrons produced by scattering X-rays. The tracks followed the pattern predicted by photon collisions. Both and Geiger independently found that scattering X-rays and recoil electrons were detected in nearly the same time. These results supported the idea that energy and momentum were conserved during each collision. The final lesson was that light cannot be described as only a wave or only a particle. It displays both types of behavior.